All right, so in this video, I wanted to go over, I guess, what exactly we mean when we talk about like the ideal gas law, like the ideal in there. What is that actually referring to? And what kind of assumptions are we making when we say that a gas behaves ideally? Because as we'll find out, right, real life is going to be a little bit different than just what we kind of assume. And so I want us to be able to, I guess, address those assumptions and see how exactly we can maybe incorporate different ideas to, I guess, give us like a better idea of like the real picture, right? The real world scenarios in which we may see gas behavior. But so to get us started, right, let's first take a look at what's called the kinetic molecular theory of gases. So this is basically a model to help us describe gas behavior using things like our atomic understanding. So like zooming in on, atoms and molecules, really just thinking about how they behave individually and allowing that to then translate to something more on the big picture scale, right? Some macro scale behaviors that we kind of like see in our lives. But so kinetic molecular theory is sort of the basis of the ideal gas law in a way. So the ideal gas law technically, came from all of these, different experiments and laws throughout history, all sort of combined together. But really, the kinetic molecular theory attempts to do what a lot of the ideal gas law itself does, but just in like a non-mathematical sense, right? In more of like a generalized, more conceptual way, right? We can sort of relate, again, all of these different products of gases in just without the math. But so to begin, right, kinetic molecular theory kind of comes from a few different postulates and assumptions and things. I've seen it summarized in like three rules. Here we'll look at it as like five postulates. The first being just a way to, I guess, describe gas particles themselves and how exactly they move about in a system. So it says right here that gas particles are going to move at random. What we really mean by that is, like if you have a gas sample, it's not all just like all of the atoms of the gas just like going in the same direction at the same speed, whatever. They are truly like randomized. They'll be bouncing off the walls, they'll be going all over the place, and right, they themselves are not really like tethered down or attached to one another in a way that would make them, I guess, like follow the leader or something. The second postulate here, which is kind of a big assumption, but something that I feel like we've already sort of thought about, has to do with the volume of the gas particles themselves. So in the kinetic molecular theory of gases, we basically say that like gas molecules are super tiny, right? They're so small. It's like literally just one atom or maybe a few atoms in a molecule. And so the amount of space that those particles actually take up is basically nothing. So, right, while we describe the volume of a gas to be like the volume of its container, the volume of like the gas particles, so like the individual molecules, we basically just say is zero. In comparison, and like the volume of the entire container that the gas may be using, right, then yeah, like that volume of the gas particles themselves is really small. And so it's essentially negligible. It's just nothing. Another assumption that we made through this theory has to do with how different particles maybe interact with one another, ignoring things like chemical reactions, right? But instead just thinking about like two gas particles meeting one another, not reacting, but instead they just kind of like get near each other, right? Those two particles are not going to experience any attractive or repulsive forces. So, right, these forces you can imagine could be arising from, say, things like charge interactions, right? When we go all the way back to way earlier in the quarter, when we first learned about like positive and negative charges attracting each other, or how like repels like. So if you have two positives next to each other, they push each other away, right? What we assume is that our gas particles are not going to do any of that kind of stuff, right? They're just like neutral atoms, neutral molecules. They're not going to say have any sort of charge attraction, and so we can kind of just assume that they'll float past each other, no problem, not slow down or bounce off any different way. That said, if two particles do actually meet and hit one another, then that causes a collision. The collision itself is not going to be anything spectacular though. It's literally just going to be the two molecules bumping into each other and then separating and going out on their merry way. So this is referred to as an elastic collision. Basically like when the two molecules just hit each other and bounce right off of each other. They don't stick to one another, like they don't hang out in the same space for too long. Instead, they just kind of do that little bounce, just like, a couple of pool balls would. This is again called an elastic collision, right? Basically just bouncing off of one another like that. This also applies to how the gas particles, I guess, collide with the walls of their container, right? We're going to assume that they're not sticking to the walls or anything like that. Instead, they just kind of hit the wall and then bounce and then continue on their little random path. The last postulate here, again, kind of has to do with stuff that we've seen or talked about before. And this is specifically referencing how kinetic energy ties into temperature for a gas sample. So specifically, it states that the average kinetic energy of a gas sample is proportional to its absolute temperature. So, right, if you increase the temperature of a gas, then you would expect to increase its kinetic energy. This again ties back to like increasing the speed of the gas. So, right, again, like ideas that we've already kind of alluded to before, now just kind of put in simply just words, right, not tied to any kind of like mathematical equation. So, right, this kinetic molecular theory is, again, just sort of taking a lot of the ideas that we already have seen and know from the ideal gas law and instead giving us just like a more conceptual approach to them. And where this becomes, I guess, more helpful is in terms of like, I don't know, explaining how two properties of a gas are related without using math. So if I ask, something, I guess, generally, like how does raising the temperature of a gas increase its pressure? Right? How does that work? Right? If you don't have the ideal gas law and you don't have just like, okay, PV equals nRT, T bigger, P bigger, then like it becomes, more of a challenge, especially to explain this maybe to like people that haven't taken chemistry, right? Or just like your friends, your family, whatever. And so instead, if you can connect it back to, this postulate right here that says that kinetic energy increases as temperature increases, right? That kind of gets us started as to connecting then how pressure is involved in that. Because if you then say like, okay, well, an increase in kinetic energy just means like the particles moving faster, we know that pressure is just like how much force a particle has when it hits the wall of its container. And so if you increase the speed of that particle, it's going to hit with a lot more force. And so with that more force, you then have greater pressure. There we didn't even need like a mathematical equation. We didn't have to solve any kind of calculation. Instead, we're just thinking more generally there. So that's what I really want you guys to be able to do with this kinetic molecular theory, or just how we describe gases, right? Taking the math out of it, are you able to conceptualize and explain kind of how these different properties are related to one another? So you don't need to like memorize these 5 postulates. Again, as I've said, like you can find maybe summaries that are just like 3 points here, but right, basically being able to, I guess, explain gas behavior without the math is like a pretty crucial part to really knowing and showing that you know kind of how gases are and what exactly we expect from them. This theory is also really helpful for us, I guess, in terms of, again, like identifying where our assumptions are when we say that a gas behaves ideally. So, right, when we use the ideal gas law, we're assuming all of these things described in the kinetic molecular theory are true. We're saying that like the gas behaves really nicely, it like bumps into each other and just bounces right off and doesn't do anything more than that. But in fact, right, some of the assumptions that are made in the kinetic molecular theory are just wrong, right? So first off, if we think about that second postulate where the volume of the gas is mentioned, right? Obviously, like gas is matter and all matter has mass and volume. And so we can't just say like, well, the gas particles take up zero space. That's just not true. Additionally, right, that third point that was made about the, I guess, attractive or repulsive forces between particles, you guys will find this out more in Chem 162, but molecules do in fact interact, and not just in like a reaction sense, right? You can have two particles next to each other and they don't necessarily seem like, they're going to hang on to one another, but suddenly like there is this attractive force that kind of pulls them together. And that force can be like kind of weak, to be honest, but it does actually contribute something. And so if we take into account, these different real gas behaviors, we're going to need to basically adjust our ideal gas law, right? The ideal gas law works a lot of the time, but it misses some key points, and we'll see exactly kind of how those points manifest and what exactly that's going to do to the different properties of gas that we understand. So getting started here, right, let's first take a look at how exactly gas particle volume is going to affect maybe our ideal gas law. So right, picture right here a sample of gas that's at relatively low pressure. So in this scenario, you can kind of see the little cartoon gas molecules. And as we usually see with a gas, right, all of the particles are pretty spread out from one another. That means that there's a lot of empty space in our container. We refer to that empty space as free volume, right? It's basically just emptiness. It's where everything but the gas is. And right in this low pressure scenario, there's a lot of free volume. But if you, say, increase the pressure and you kind of push down maybe the lid of this container and really press those molecules closer to one another, right, with that higher pressure, the free volume becomes less and less. And the volume of the particles themselves are actually becoming like much more of a significant part of the space available. So, right, at these higher pressure circumstances, when you do have maybe much less empty space in there, the volume of the gas particles is going to essentially add on to the ideal volume of the gas, right? They become actually more important. And so in a real gas, we expect to see a slightly higher volume than what we would assume in an ideal gas. So, right, that kind of handles that first assumption made in the kinetic molecular theory. But let's look at also the second assumption, which had to do with the way that, different molecules are maybe attracted to one another. So again, you'll learn more about this if you take Chem 162, but basically, what goes on, right, when you have like two particles close to one another is that those two particles are always going to experience some attractive forces between them. So, right, no matter what they are, they're going to try to kind of pull each other together, and these are referred to as intermolecular forces, or IMFs. Now, the IMFs themselves, as I mentioned, are kind of weak, but the strength of them does kind of increase with certain factors. So, for instance, if you have, say, a larger gas particle, that larger particle is going to experience more intermolecular forces. So, right, bigger atoms or heavier molar masses, those all correspond to then stronger attractive forces. Additionally, if the molecule itself is polar, meaning that the electrons that are maybe shared in a covalent bond are not equally shared, right, in that case, kind of what happens there is that one side of the bond ends up being more negative than the other side, right? I think we introduced this when we first learned about like water and how it worked so well as a solvent because it's a polar molecule, right? So other molecules too can be polar, and what that kind of does then is it gives the molecule not necessarily like an ionic charge, but a partially positive or a partially negative charge to it. So, right, two sides of one molecule are going to be kind of opposite in charge, and because of that, right, if you have, say, a molecule with kind of a plus side over here and another molecule with a negative side over here, right, they're going to be attracted to each other as well. And so those polar molecules also then experience much stronger intermolecular forces. Now, what that then means in terms of like what we see with the gas or how it behaves, right, we can kind of picture right here. So imagine basically you have, a gas molecule hitting the wall of its container as gas molecules do. And that's what causes then like the pressure of the gas. Now, if that molecule is instead kind of held back by its neighboring molecules, right? Maybe these other particles are nearby that are kind of attracting the particle away from the wall, right, then that kind of means that it's not going to, I guess, hit the wall with as much force as it would if those other particles just weren't there or weren't pulling it away. So right through this attraction between the different particles, I want us to think about how this would affect then the pressure that the gas exerts. So you guys don't have to do like a quiz or anything on this, but I'll just kind of bring it up here, right? Think to yourself how the pressure of a real gas would compare then to the ideal gas pressure. So right, kind of reasoning through this, so if these other particles are around and they're kind of pulling their neighbor away from the wall, right, what that does is it weakens the force that that neighbor has and it weakens the pressure of the gas. So that's to say then that the real pressure or the pressure of a real gas is going to be less than the pressure of an ideal gas. And so, right, this presence of intermolecular forces results then in a lower real pressure than what we'd see maybe in our ideal gas law. Now, this effect is actually much more exaggerated in high pressure scenarios, right, where you do have like your particles much closer together, so then they kind of have more opportunities to attract and pull away each other. Also in very low temperature scenarios where maybe your gas particles are just moving a lot more slowly, right? They have more time to attract and interact with their neighbors. And so while it's always true that a real gas has a lower pressure than an ideal gas, this effect is really exaggerated when pressure is higher or temperature is lower. All right, so let's put these things together. So as we've already said, right, when we account for real gas behavior, we're going to need to change both the pressure and volume that we assumed in the ideal gas law. So right, because a real gas is going to have, say, a lower pressure than is ideal, right, we would need to kind of add some kind of correction to make it equal. Or with the volume of a real gas, right, because that is generally higher than the volume of an ideal gas, right, we would need some sort of correction to lower that volume as well. So I kind of outline that here as just like the pressure of a real gas plus some correction is going to be equal to the pressure of an ideal gas, or the volume of a real gas minus some correction is equal to the ideal volume. We can then sort of take that and replace then our P and V values that are within the ideal gas law and give us, instead of an ideal gas law, basically like a real gas law. Now, the real gas law is a little bit more complicated than just like, say, these general correction terms. It's instead written out right here as the van der Waals equation. But right, this equation basically works as our real gas behavior connection between pressure, volume, number of moles, and temperature. So within this equation, right, the different symbols are all the same things that we've seen before as far as PV equals nRT. The only kind of new different thing that's in here are our new variables A and B, which are these van der Waals constants, which are, experimentally found and specific to, a certain substance. So that's to say, like, hydrogen has a certain A and B value, and oxygen has a different A and B value. These different values I have listed right here. We've got, a whole slew of different ones to choose from, but right, you can see kind of how, some substances are going to have, say, much higher A and B values than other ones. Specifically, I want to highlight kind of how this again relates to some of the ideas that we saw before. So as far as like those correction terms, right, and when they become most relevant or most needed, for things like intermolecular forces, for a molecule that experiences more intermolecular forces, it's going to need a bigger correction term in its A constant. So for instance, right, some of the, say, heavier gases that are in this list, like bromine, right, or Br2, that has like a pretty high molar mass. And so that should have then a pretty high A constant associated with that. You can find that kind of right in the middle of this table right here, right? For Br2, it has a really high A constant. But these different constants, right, are not expected for you to memorize or anything. These would be provided to you for an exam or a question, on your homework. But right, I just wanted to kind of show a selection of them right here in case you wanted to reference any of them. Right, so let's see one example using the van der Waals equation and kind of seeing how important it truly is. To do that, I first want us to just look at an ideal scenario instead and kind of use that to maybe compare to the van der Waals equation and how that would make a difference. So consider here 215 grams of carbon dioxide gas in a 1.98 liter container at 26 degrees Celsius. So assuming ideal behavior, right, what would be the pressure in atmospheres of this gas? So as usually is the case, right, we're going to need to use our PV equals nRT equation. Solving for pressure, that's equal to nRT over V. And so, right, we're told things like the volume as 1.98 liters, the temperature as 26 degrees Celsius would instead be 299.15 Kelvin, and the number of moles, because we're starting with 215 grams, we can then convert that into moles using CO2's molar mass. We find that that's equal to 4.88 moles of CO2. And so we can plug that into our PV equals nRT equation. Solving for pressure, we should get 60.6 atmospheres. So assuming here ideal behavior, everything is, going fine, we're making all of these assumptions and stuff. This is what the pressure of the carbon dioxide should be. Then what I want us to do is compare what the real gas pressure would be. So instead, assuming real gas behavior, what is the pressure of that same sample? So this time we're going to use the van der Waals equation. We're going to need the van der Waals constants for CO2, which I pulled out from my previous slide. So A and B are written up here. And right, we're going to apply these different properties of the gas into the van der Waals equation, solving for now pressure. Now I recognize that this equation is a little bit of a beast, right? I've taken up a lot of space here so that we can work out the entire thing. But I do want to highlight kind of some of the similarities between this equation and the ideal gas law, right? We can use basically the same volume, temperature, and number of moles that we found in the previous example. So we already know V, T, and N in this equation. We have A and B given to us. That really does help us isolate it all down to just finding the pressure. So, right, setting this up, I'm basically just going to plug in all of these different values for volume, for number of moles, etc. And what I get then is this massive, massive equation. So I recognize that this is huge and a lot. And I recognize too, like, the ideal gas law already had so many variables in it. Man, why did we have to make it more complicated? But this is again to show us just how much we're kind of missing out on with the ideal gas law. So here I've just placed in all of my different values, my different units and things like so. And I'm not going to try to, I guess, rearrange things to just solve for pressure. There's so much algebraically going on here. I'm just going to work through this kind of piece by piece. So what I mean by that is like simplifying this equation down in steps. So I know like it starts off with pressure plus whatever. That whatever is like everything that's in the fraction. Now I want to still like kind of take it piece by piece, bit by bit. So I'm just going to do the numerator first, kind of solving for that. So taking 4.8854 squared and then times 3.658, that gives me then 87.305. Now the units that are kind of left over here are going to be atmospheres liters squared, right? You can kind of see how like the moles squared would cancel out with the units that are within A, so those moles sort of disappear. That leaves us then just atmospheres liters squared as the numerator of this piece. The denominator is, the volume squared, so 1.98 squared should be 3.92 liters squared. And so, right, again, just kind of trying to, I guess, piece through this bit by bit. So that kind of handles, I guess, part of the first section. I can then kind of continue on with my equation. So I'm not going to change the volume yet. I'm instead going to solve for the N times B, so number of moles times B should be equal to 0.209 liters now. And then I can follow that up with equal to N times R times T. So again, just kind of like trying to chomp through this like bit by bit. That way I don't get lost in all of the math involved here. Then taking this to the next step, right, I might try to simplify things down a little bit further and say this fraction here of the 87.3 divided by 3.92 is equal to 22.269 atmospheres. Then, evaluating out the volume minus 0.209 liters gives me now my adjusted or corrected volume as 1.77 liters. And then that right side of the equation is just going to stay the same. Now, finally, I'm looking at something that looks a little bit more manageable math-wise, so I'll just divide both sides by 1.77 liters. That will then give me the pressure plus 22.269 atmospheres as equal to 67.737 atmospheres. And then finally, I can solve for pressure itself as equal to 45.468 atmospheres, or rounded off to 3 sig figs, 45.5 atm. So right, this is, again, like I said, like pretty massive equation, pretty tough to work through, especially if you're like intimidated, but right, take it piece by piece and it should be totally fine, right? This is just like basic algebra. You're just plugging in all of these different values. But I really want to point out here, right, just how much different this pressure that we found, assuming real behavior, compares to the ideal gas law version that we just solved. Right, previously we said that the pressure of the CO2 was 60 atmospheres. Now we're saying it's 45 atmospheres. That's like a whole 25% less. So the ideal gas law really does make some big assumptions, right? And those can give you wildly different results from what you like actually see in the real world. And so I wanted to highlight that just to kind of show, I guess, how exactly the real behavior versus the ideal behavior can be so much different. All right, but so we'll see some other examples kind of using the van der Waals equation, using those van der Waals constants, but please let me know if you have any questions, and I'm always happy to help. Bye.